Hi, my name is Ho-Chang Lee, and today I'll be talking about our work on learning fingertip force to grasp deformable objects for a soft wearable robotic glove with tendon sheath mechanism. Soft wearable robotic gloves driven by tendon sheath mechanisms are widely developed for assisting people with a loss of hand mobility. To aid users to grasp objects of various physical properties, the wearable robotic gloves must apply an appropriate amount of force to the objects. For example, consider a case in which a user wearing the robotic glove tries to hold a flexible cup filled with coffee. Without the proper control of fingertip forces applied to the cup, the robotic glove can cause spillage of the contained liquid and harm the user. Therefore, knowing the forces generated at the fingertips is a key factor in successful object grasping. However, attaching various sensors to the glove may not be desirable, as it requires individual calibration and even poses safety risks in aqueous environments. Thus, this paper presents a learning-based approach that incorporates information about object stiffness to estimate fingertip forces applied to the deformable object, using only the data from actuation system. Furthermore, the applicability of our method was evaluated by estimating the fingertip forces applied to common daily items and performing real-time force control. This figure shows the nonlinearity between motor encoder values, flexion wire tensions, and fingertip forces. It can be seen that the nonlinearity among the parameters and hysteresis are subject to change depending on the object stiffness. Here, the black line represents the data for the object with the lowest stiffness, while the blue dotted line represents the data for highest stiffness. Figure A shows that as the stiffness of the grasped object decreases, both the flexion motor encoder values and the flexion wire tensions increase. Figure B shows that lower the object stiffness, the more deformation occurs, subsequently causing greater changes in motor encoder values. Finally, figure C shows the decrease in stiffness causes a decrease in fingertip forces measured, but incurs higher flexion wire tensions. From this, it can be seen that fingertip forces can greatly vary depending on the object's stiffness, making the force estimation difficult. For our experiment, we developed a tendon sheath mechanism-based soft wearable robotic glove. It is made from flexible polyamide material, and the wires passing through the rings fitted near the joints of the fingers facilitate the grasping and releasing motion of the hand. Our wearable robotic glove has a portable actuation system that can be worn on the forearm. At the distal ends of the actuation system, the load cell measures the wire tension during flexion and extension of the fingers. We created 6 deformable cylindrical objects from silicon mixtures and 1 3D printed rigid object for testing. During the experiment, a user wearing the robotic glove grasped and released each object 80 times to collect the training data. The applied fingertip forces, motor encoder values, and wire tensions are collected to train and validate our model. The stiffness of each deformable object was measured using a CNC machine equipped with a force sensor. For the daily objects, such as a paper cup and tennis ball, no training data was collected. We did this to test the feasibility of our model on estimating the forces applied to untrained objects. To estimate the fingertip forces applied to objects of varying stiffness, we propose stiffness-aware temporal attention long short-term memory, or as we would like to call it, SATA LSTM. SATA LSTM comprises 2 main models: stiffness estimation model, as highlighted in red, and force estimation model, highlighted in blue. The initial inputs to both models are the information from actuation system, which include wire tensions and motor encoder values. First, the stiffness estimation model estimates the object stiffness, and estimated stiffness is concatenated to input and a hidden layer of the force estimation. The force estimation model comprises 2 LSTM layers that retain information of object stiffness and a temporal attention network. The temporal attention focuses on important time steps within the input sequence, which contains actuation system data and the estimated stiffness. This is the temporal attention network which we utilize to focus on the important time steps of the input sequences. The input of the temporal attention, which is also the hidden layer features of LSTM, contains knowledge of the data from the actuation system with object's estimated stiffness. The query feature is calculated as the following equation. Here, W and B is trainable parameters. Then, attention for each time step is calculated using the query feature. Finally, attention-enhanced hidden state feature is fed to a fully connected layer to estimate the fingertip force. The figure depicts the fingertip force estimation results for 3 deformable objects of varying stiffness and a rigid object, using 3 different algorithms. As it can be seen from the figure, the fingertip force estimation using LSTM without stiffness as information tends to deviate from the actually applied forces. Especially, this model shows drop-offs in force estimation in the regions that the applied forces are increasing. LSTM plus stiffness model, which is the LSTM model with estimated stiffness only appended to the initial input, shows some improved performance, but still displays noticeable differences from the ground truth. Finally, our model, SATA LSTM, shows the most accurate estimation among the compared models. This shows that incorporating the stiffness information to the hidden layers and incorporating temporal tension has increased the performance of our model. The performance of SATA LSTM was evaluated by comparing it against 5 different learning-based models, which included linear regression, random forest regression, a model with fully connected layers, LSTM model, and LSTM model with the estimated stiffness only appended to the initial input. The fingertip force estimation results are summarized in the table to the right. In this table, our SATA LSTM yielded the highest accuracy in estimating the fingertip force. Compared to the LSTM model, LSTM stiffness showed 26% improvements in RMSE, while our model, SATA LSTM, showed 49% improvements in RMSE. Furthermore, our SATA LSTM was evaluated on a reassembled actuation system to test the robustness of our method. As shown in this table, SATA LSTM has the least variance from the original results, while other models all doubled the original result. To evaluate the applicability of our study, we tested our model on some deformable, untrained daily objects and conducted real-time force control. We chose 2 daily objects with relatively low stiffness, which is the cup, and high stiffness, which is the tennis ball. Figure B shows the prediction results on 2 daily objects, resulting in RMSE of 0.88 newtons and 0.54 newtons respectively. Also, real-time force control was done on deformable objects with relatively low and high stiffness. Figure C shows the results of real-time force control. After reaching about 90% of the target forces, our model resulted in MAPE of 5.1% and 2.1% respectively. This video contains the results of the fingertip force estimation performed on objects of varying stiffness. In this study, we showed that our proposed model, SATA LSTM, accurately estimated the applied fingertip forces for objects of varying stiffness and outperformed models that do not consider the object stiffness. Also, our model successfully predicted the forces applied to untrained daily objects and controlled the amount of forces applied to relatively soft and hard objects. From the following results, our research showed that incorporating object stiffness is a crucial factor in determining the forces being applied to deformable objects. For future works, our research can be extended to incorporating our model with methods that detect users' intentions. So while grasping a deformable objects based on users' intents, our model would be utilized to provide appropriate grasping forces to the object. Thank you for listening to our presentation.